So subatomic particles. Subatomic means below atom, smaller than the atom. All atoms are composed of the same subatomic particles: protons, neutrons, and electrons. There are others that particle physicists are interested in. We don't talk about them in general chemistry. Stick with the three big guys. So protons and neutrons have nearly identical masses. Here are their actual masses, and I messed up. Those are subscripts, superscripts. The mass of the proton, 1.67262 times 10 to the minus 27 kilograms. Mass of the neutron, the first three digits are the same, times 10 to the minus 27 kilograms. They are not exactly the same in mass, but for most purposes, we can think of them as being the same mass. The electron, on the other hand, is much smaller, 9 times 10 to the minus 31 kilograms. So here's another illustration. If the proton had the mass of a baseball, an electron would have the mass of a grain of rice. So electrons, really small compared to the protons. You do not need to memorize these numbers. What I want you to know is that the proton and the neutron are about the same mass. Electron, much, much smaller. Well, a common unit that we use to express the masses of things like protons and neutrons is the atomic mass unit. A unit like kilogram or even gram isn't very useful because it's way too big. It's like measuring the distance between Reedley and Fresno in inches. It's just not a great idea. So they came up with a unit. They were very creative in naming it. It's descriptive, though. Atomic mass unit. This is a mass unit for measuring things on the atomic size. And the abbreviation for it is AMU. We pronounce it AMU. It's not AMU, some odd relative of an emu. 1 AMU is defined as 1/12 the mass of a carbon containing 6 protons and 6 neutrons. And what that ends up being is that the mass of a proton or a neutron is approximately 1 atomic mass unit. So this carbon atom with 6 protons and 6 neutrons in its nucleus, there are 6 plus 6 equals 12 of these particles that have mass. So what we're doing is we're defining that atom weighs exactly 12 atomic mass units, 6 protons and 6 neutrons. And so then 1 atomic mass unit is 1/12 of that. They used carbon-12 because it's stable, it's safe, it's cheap, it's easy to get a hold of. They could have chosen something else, but they chose something easy. The charge of a proton and the charge of the electron are equal in magnitude but opposite in sign. So we can give their charges in coulombs, which is the unit of charge, plus 1.60218 times 10 to the minus 19th coulombs, and minus 1. But we don't actually use that number in general chemistry. We just say, well, a +1 charge and a -1 charge. So relative charges, you should know these. Proton has a +1 charge. The neutron is neutral. It has a 0 charge. The electron has a -1 charge. Here are the actual masses in kilograms, which you might need to look at that for a homework problem. Don't memorize those. I don't remember what they are. Mass in atomic mass units. Basically 1, basically 1, basically 0. Okay? So that's what you should know. Yes?
Any units
for charge? Well, these charges have the unit C, coulomb. These are relative charges. So this one relative to that one, this one relative to that one, and so this does not have a unit. So it's not good for like physics calculations, but all we're looking at is the total charge of an atom or of an ion. And so that's what we're interested in, is the relative numbers of protons and neutrons and electrons. Any other questions? Most matter is charge neutral, meaning it doesn't have an overall charge, because protons and electrons are usually present in equal numbers. So this paper doesn't have an overall electric charge on it. That tells me that the number of protons is equal to the number of electrons in this particular piece of paper. You can develop a charge imbalance. This can happen, it doesn't happen as much around here, but I grew up in the Midwest where in the winter the humidity is really, really low. And so you walk around in your stocking feet on the carpeting and then you touch a metal door jamb and you get shocked, a little electric shock. Last time I visited my parents, I was trying to go to sleep and there were no lights on in the room. And I kept thinking I saw these little flashes of light and I'm like, am I hallucinating? What is going on? And then I realized that when I rolled over, there was static between me and the sheets. And I was seeing little tiny bits of static electricity in the dark. And I'm like, wow, that's really dry air. Doesn't happen to us as much around here. But if you take a balloon and you rub it on your hair, right, and then you pull the balloon away, your hair will follow it. That's because of static charge, static electricity. Static can build up and cause an explosion at the gas pump. That's why they want you to fill your portable gas can on the ground instead of in the air or in the back of your pickup or something, to avoid static charge buildup. Another example of charge imbalance is lightning. So negative charge builds up in the clouds, positive charge builds up on the ground, and the lightning is an equalization of that electrical charge. The negative charges coming down to the ground to equalize the charge. Then that's what the static electric shocks are, is you've got an imbalance. One thing is positively charged, one is negatively charged, and they don't like that. They don't like to be separated, and so the electrons will jump from one thing to another. Any questions? The number of protons in the nucleus of an atom is important. It is what defines the element. So I think of it, the number of protons as sort of being the personality of an atom. I like to personify atoms. Makes it, I don't know, more fun. If you think about people, you can change your hair color. You can dress up in a costume. You can get tattoos. You can do all kinds of different things. You can have cosmetic surgery, get your teeth straightened, all sorts of different things you can do to your outside body. Does that change who you are? No, it doesn't. Your personality, your soul is the same regardless of what you do to the outside. Now, doing something to the outside might make you feel better. There's nothing wrong with that. But it doesn't change who you are. The protons are like the personality or the soul of an atom. The protons define which element it is. The electrons can change. Sometimes you can even mess around with the neutrons. We'll talk about that. But the protons define which element it is. So they call that number of protons the atomic number. It's given the symbol Z. Don't ask me why. They just did that and we have to go along. So here we have a picture. Here we have helium. In a helium nucleus, there are 2 protons. Every single helium atom has 2 protons in its nucleus, no exceptions. If it only has 1 proton, it isn't helium. Carbon, the graphite in your pencil. Carbon nuclei all have 6 protons. So on the periodic table, this information is provided. Here we have the chemical symbol. Here we have the name of the element. And above the chemical symbol is the atomic number. So here we looked at carbon. Carbon has 6 protons. It's element number 6 on the periodic table. Here's helium. It has a 2 above it. That tells me that helium has 2 protons in its nucleus. Go down here. W is tungsten, 74 protons. It's right there on the periodic table. You don't need to memorize atomic numbers because any reasonable chemist will always have a periodic table available. I have one on my phone because, I just feel better. Always knowing I can look up the atomic number of anything anytime I want, right? So the periodic table. On the periodic table, each element is identified with a unique atomic number and a unique chemical symbol. And these element names and symbols are one of the things that I quizzed you on with that memorization quiz this morning. At noon. It wasn't this morning. The chemical symbol will either have one or two letters in it. The first letter is always capitalized. The second letter is never capitalized, if there is one. So as an example, the chemical symbol for helium is capital H, lowercase e. And I know that some people like to write in small caps. You can do that everywhere except when you're writing metric prefixes and element symbols. So you don't write it like this. That's wrong, not acceptable. Make your lowercase letters. Most of those chemical symbols are based on English names. I mean, HE for helium makes sense. It's the first two letters of the word helium. The chemical symbol for carbon is C. That's the first letter of carbon. Ca, calcium, well, we couldn't use C because it was already taken. So for calcium, we use Ca, the first two letters. But some of them are based on Latin names, and those are the ones that are tricky. Like, how do the heck they get Na for sodium? There's no N or A in the word sodium. Why not SO? Well, it's from the Latin name, natrium, which means they isolated it from the ocean, the sea. So it's Na for natrium. We call it sodium. You just have to deal with it. Just like you have to do with irregular verb conjugations in the English language. So we need to know those symbols. So all atoms of a given element do have the same number of protons. They don't necessarily have the same number of neutrons. The number of neutrons can vary. And this is where one of Dalton's ideas in his atomic theory needed to be adjusted, because he said all atoms of a given element are identical. And now we know it's not true. They have an identical number of protons, but they can have different numbers of neutrons. So if you have two atoms or more that have the same number of protons but different numbers of neutrons, they're called isotopes. Iso is a prefix that means the same. So isotopes. And as an example, neon. There are 3 isotopes of neon. All of them have 10 protons. But some of them have 10 neutrons, some have 11, and some have 12 neutrons. All of those exist, and they're each going to have a slightly different mass, right? Because the neutron has a mass of approximately 1 atomic mass unit. So you throw a couple extra neutrons in there, you're going to change the mass of the atom. Just because there are 3 different isotopes does not mean there's an equal number of each of them. Most elements have one isotope that is more abundant. There's more of that, and then there's just a smaller percentage of the others. The relative amount of each isotope in a naturally occurring sample is relatively constant. It doesn't change much, whether you got your helium from the balloon store, or whether you got it from the scientific supply store, or whether you went, and isolated it from the air. It's going to have the same relative amounts. And it's usually expressed as a percentage, and they're called natural abundance. So the natural abundance of an isotope is what percentage of the total isotopes are that particular isotope. If we take the number of protons and neutrons in an atom and add those together, that's called the mass number. And that's represented by the symbol A. I would have used that for atomic number. Doesn't that make more sense? Atomic number, atomic starts with A, make that A. No. They made that Z, and this is A. So that's going to be confusing, but it's not going to be a big issue. So A, the mass number, is the number of protons plus the number of neutrons. So when we have multiple isotopes that we're dealing with, we have to be able to specify which one we're talking about. One way is to use nuclear symbols, and they take this general form, where the capital X here is the chemical symbol, the 1 or 2 letter abbreviation for that element. And then on the left, we have a superscript that is the mass number, and a subscript that is the atomic number. So these 3 isotopes of neon, they all have Ne the element symbol for neon. They all have 10 protons, but they have different numbers of neutrons. The number there, that 20, is not the number of neutrons, it's the mass number. To figure out the number of neutrons, you take the mass number and you subtract the number of protons. And so that one's got 10 neutrons. And this one has 11 neutrons. And this one has 12 neutrons. That's how I remember which number to put on top and which one to put on the bottom. I put the big one on the top, the small one on the bottom, and it's all stacked up for you to subtract. Two other ways to notate which isotope we're talking about. One is to use the chemical symbol, the element abbreviation, followed by a dash with the mass number. So you could have Ne20, Ne21, Ne22, or sometimes we'll write out the whole name of the element. Neon 20, neon 21, neon 22. Any questions? So here's a table from your textbook. The symbols, so we've got neon 20, 21, and 22, or they could be indicated this way. They all have 10 protons. They have differing numbers of neutrons. And you get this number by taking the mass number and subtracting the atomic number. The natural abundance is not something that you can get from these symbols. This has to be measured experimentally. So it turns out for neon that 90.48% of all neon atoms are neon 20. And there's just a little tiny bit of neon 21 and less than 10% is neon 22. So you would never ever memorize those numbers. Waste of brain space. Okay, so what kinds of questions could be asked about this? What are the atomic number, mass number, and symbol for the carbon isotope with 7 neutrons? Well, start at the beginning. Atomic number. How do we find the atomic number for carbon? We're going to look for carbon on the periodic table. 6. So the mass number is 6. I'm sorry, the atomic number is 6. What's the mass number? You get 12, 13, and 6. The mass number is the sum of the protons and the neutrons. Right? So we know it has 6 protons, and they're telling us that it has 7 neutrons. So the mass number is 6 plus 7, 13. And then the symbol. So we'd put a C here. We put the mass number as the superscript and the atomic number as the subscript. So we could indicate it that way, or C-13, or carbon, spell it right, carbon 13. Any questions? How many protons and neutrons are present in an atom of this? 19 protons and 20 neutrons. So the protons is just, they flat out tell us right here, 19. If they didn't write the 19 down there, you could find potassium on the periodic table, it's element number 19. And then to find the neutrons, we're going to subtract 39 minus 19. So 20 neutrons. Any questions? So we can have atoms of the same element that have differing numbers of neutrons. And then the electrons are on the outside. I think of the electrons as being a little bit like your clothing. It's pretty easy to change your clothes and look like a different person, right? You could show up in flannel pajama pants and a ratty old t-shirt, or you could show up in a power suit, right? You're going to appear different to the world. So that's like atoms gaining and losing electrons. The number of electrons in a neutral atom is going to be equal to the number of protons. So if a carbon atom has 6 protons, it has 6 electrons, because overall it's neutral. If an atom gains electrons, it's going to have more negative charges than positive charges. And so overall, it's going to have a negative charge. Negatively charged ions are called anions. Positively charged ions are ones that have lost electrons. Now they have more protons than electrons. Positive charges, those are called cations. So cations have positive charges. I remember that because I like cats. If you don't like cats, that isn't going to work for you. I have positive feelings for cats, so cation are positive.